Howdy, everybody. I thought I'd just give a quick rundown of how I solved day 6 of Advent of Code in Haskell. That's the functional language that I'm trying to learn with this. I'm still really new, right? I only had done like a week of Haskell beforehand. I've done some Lisp and stuff, so I haven't been able to solve every day in Haskell, but this one I was able to solve. Probably because the problem itself lent itself to a functional approach, or at least I understood how to do it functionally, would probably be the best way to describe it. But let's just go ahead and look at it so you can see what I did. Nope, that's not it. The idea was you were given these times and distances for a boat race that you were doing, and this was the time. The top was the time you had in the boat race to do it, and the bottom was the current fastest time. And the goal was can you determine how many ways can you beat the fastest or beat the farthest distance. And the way you do it is you use a tow. It's a toy boat that you push a button, and that kind of winds it up, and then you let it go. And the idea is for every millisecond you hold the button down, your thing goes 1 millisecond faster. So it had this kind of breakdown where it said if you hold it down for 0 milliseconds, it won't go anywhere, and that'll be the end of the race. If you hold it down for 1 millisecond, so if the first race was 7 and you hold it down for 1 millisecond, you now are going 1 millisecond for 6 seconds. And you can only push it down once. So it's just how long do you hold it at the beginning, and then the rest of it is how fast it goes with the rest of the duration. So in this case, just to iterate or go through a couple more, if you hold down the button for 2 milliseconds, that's the first 2 milliseconds of the race. You now have 5 seconds left in the 7-second race, but you're now going at 2 millimeters per millisecond for 5 seconds, which gives you 10. The next one, if you hold it down for 3, 4 times 3 is 12, and then if you hold it down for 4 times 3 is 12. 5 gives you 10. And the question they're asking is how many of these beat the 9? Well, in this case, it happens to be 4 beat the 9 here. And so you're going to do that for each race and multiply them together. So this one has 4, and then the next one has 8, and the next one has 9, right? 4, 8, and 9. So the idea is you're just doing these races and trying to find out how many ways you can beat it. And once you figured out how many ways you can beat it for each of the races, you multiply those together. So that turned out not to be, again, I'll link to the problem in the thing so you can read it more if you don't quite understand. But the idea was actually not too tough. So if we start in my main block, I just read the input file, and then I used parsec again to parse the lines with my parser. That wasn't too tough. Basically, both the lines are the same. If you look at my parse input line, I realize they're both the same. Basically, I just have I can do the mini one for whether it's time or distance, then the colon, and then some number of spaces to get me to here. And then all the integers are just a mini one of digits separated by spaces. And so I can mini 1 digits separated by spaces. That's the way to describe it, right? It's this separated by this. And turn those into integers, you get an array of ints. I had a little trouble getting to the parsing. I still haven't quite figured out how this works, but it is easier for me to write like a parser function right here that did that for the input line and returned the integers. But once you have the integers, because they're together, you can just use a function like zip, which I used in Rust as well. And then so I just zip the two lines, and now I can do for the solution. I can do the product of mapping my winners function to that zipped list, right? So for each of the items in the list, I call the winners function, and then I do a product of all of those together, and that's P1. So that was my initial solution, which was this, and it turned out not to be too hard, right? The way you calculate a winner, at least for my naive solution, was just brute force. I'm going to go through from 0 to time, just like they did here in their example. Start at 0. The zero being how long you hold it, right? So hold down the button 0 milliseconds, and you do that for all the way to 7 milliseconds, the end, and figure out how much of them win. How many of them win. And so how do you figure out if they win? I just use these two functions. The calculate distance function is if you give me a total time and your current time, this is how you can calculate how far you got. It turned out to be a pretty simple math problem in that respect, where you say, oh, well, if I've used 2 seconds of the time, I now have 5 seconds, which is the total minus the 2, that I'm going this speed. So it's just total minus time times time. And then you have the winner function, which is calculating the winner, where you call this calc distance, and if that's greater than the current distance, you return a 1, otherwise you return a 0. So to calculate the winners in that respect, then it's not any more difficult than to just say, okay, I'm just going to map over the all the times and call that winner function and sum them up, right? I'll either have winners or losers, and I won't do it. And that worked pretty easy, part 1. So part 1 wasn't that tough, right? I think it was pretty easy. I did struggle in Rust with the parsing compared to the parsing in Haskell, which was kind of funny. I don't know why, but this just seems more natural. I did copy and paste, so maybe that doesn't count totally. But anyway, we'll move to part 2 of the solution. Was they said, oh, it's actually a kerning issue, which is like a spacing issue. Basically, you ignore all the spaces right here. So instead of having 3 races, you actually only have 1 race, and it's this giant number. And in Rust, the brute force solution actually was able to solve it. I got a stack trace, though, when I was doing it in Haskell, and I think the reason is, right, if you're doing it 71,530 times, like the lists get pretty long. I don't know, maybe I was doing something wrong. There still may be a way to do it in Haskell to solve it quicker, but just with my naivety, I had gotten slower, or I was getting stack traces, and so I went to, in Rust, I discovered a faster solution. Maybe I can just write it out really quick for you guys to see. The general idea is when you're doing these races, like this is, you have the T0 right here, and then you have Tn right here, which is your total time. Well, that is a terrible line. I'm going to draw that one more time for you, and it will be nearly as terrible, but at least a little bit better. So when you have this range right here, when you have all these races, if you looked at the solution and if you thought about it, there's kind of this, I think it was a bell curve. It turned out to be the quadratic equation, but there's like this point where you start winning, and then there's this point where you are no longer winning. So like there's this range in here, and the way that I thought about it was, at least for me to solve it, was, oh, well, I actually only need to calculate from here to here, and then here, going backwards from here to here, and then my winning number is actually Tn minus these 2 chunks, right? So I can just do minus, Wn, let's say that this is x1 and x2. You'd be x1 plus x2, right? And so at a high level, that's kind of how it works is, oh, I only need to go to here and I only need to go to here to solve the problem. That did not produce the stack trace, but it also wasn't super fast. But at least in Haskell, it was way faster in Rust, because it meant, like, instead of trying to solve millions of them, you're only solving, some small subset. In fact, if I look at the Rust solution, I may still have it. right here, you can see that it took about half the time in here and a fifth of the time in part 2, but also the number of iterations I had to do, like the number of calculations, as I went. The faster algorithm that I just talked about is only 10 million, where the other one is 46, right? So you're doing like a fifth of the calculations. That was fast enough where I was like, now I'm solving it in millisecond times, and I didn't feel so bad. So it turned out not to be the optimal when we looked later. It turned out it was you could solve it with the quadratic equation, which is funny. I actually remember it from junior high, but I don't think I would have ever gotten to using it in this solution. Anyway, so how does that look? How do I turn this idea into code? Well, I have like a winners to and a winners from, where I basically am just doing a take while. I'm still calculating the distance. I'm just doing a take while, and then I do the length of that first section, and then I do a winners from, where I do the same thing, but I do it in reverse from time to 0. Until I'm losing, as long as I'm losing the race, right? Eventually I'll start winning, and that's the length. And then, so winners faster is just, again, time minus the sum of those two times plus 1. And it ended up being off by one thing related to like exclusive versus inclusive lists. Anyway, I probably could have actually done this in one function in Haskell, now that I think about it. If you look, it's the same thing. It's just a difference between the two mappings. And so I could have done like a winner's iter that is just this part of the code or whatever. Sorry, this part of it from here to here. And then just passed in this versus this. But I wanted to get this out and show you my solution. I did get it to work. It's not perfect, but the part 2 still took a few seconds, even though it was like using the winner's faster one. But I think it felt really good. I would be interested to hear from all you Haskell aficionados, why did it take a few seconds when a similar algorithm in Rust just took, microseconds to run? My inclination is it has to do with the length thing. Like, this take while is going to produce an actual list of this, and so in the part 2 phase, that list is actually quite big, right? And so it actually has to calculate all that disk list and then do the length. So there might be a faster way to do that. I don't know if recursion would work either. But anyway, I would be interested in seeing your solutions in Haskell and how it was simplified, how you were able to solve it in relatively fast time. Obviously, if you used the math trick, that's cool. I'd like to see that as how you did it. But I'd be most interested is if you didn't use the math trick and you did something along these lines or some other way to reduce the problem set. I'd be interested to see how you did that, or maybe even how you might improve upon the way that I did it using some cool Haskell thing that I don't know. Yeah, just one more time, I really appreciate the input that you guys are giving me, especially in the Haskell parts, helping me learn this stuff. But just anything in general, I always love learning more, and one of my goals in sharing these videos is that I learn from it and you guys learn from it. We all kind of get better at programming while we're having fun in advent of code, and in the future maybe just programming in general. So anyway, I think that's it. I hope you're enjoying your advent of code, and have a good day.